How does lift work? How airplanes fly? An airliner at the end of a runway looks like a machine arguing with common sense. It carries fuel, luggage, food carts, water tanks, miles of wiring, engines, metal, composites, and hundreds of people settling into seats as if they are sitting in a building, not something about to leave Earth. Then the engines push harder. The runway begins to blur. The nose lifts, the tires stop touching concrete, and the whole impossible weight rises. It does not happen because the airplane is light. It happens because the wings have shaped the air into something powerful enough to hold up a giant. Long before airport ramps filled with jetliners, people had already noticed that air could carry things. Kites made the lesson visible. A thin sheet of fabric or paper pulled against the wind at the right angle could climb into the sky and pull back on the string with a force you could feel in your hand. Sails showed it too, swelling in the wind and moving heavy boats across water. Leaves twisted as they fell. Birds glided between trees. Even a flat piece of wood held out of a moving carriage could suddenly tug upward or sideways. Air looked empty, but it was never nothing. It pressed, curled, dragged, lifted, and pushed back. For centuries, the idea of human flight lived in the messy space between careful observation and hopeful guessing. People watched birds open their wings and imagined machines covered in feathers, flapping frames, and fragile gliders built from wood and cloth. The challenge was not simply finding enough power to move forward, it was figuring out what a wing was doing in the first place. A bird was not just beating the air like a fan. Its wing met the air at an angle, bent the moving flow around its body, and left a stream of air pushed downward behind it. Somewhere inside that downward motion was the upward force that kept the bird in the air. One of the important figures in turning flight from fantasy into engineering was Sir George Cayley, who helped describe the different forces acting on a flying machine. Weight pulling down, lift pushing up, drag holding it back, and thrust driving it forward. That separation was a major step. It gave experimenters a cleaner way to think. Instead of treating flight as one mysterious act, they could break it into pieces and study each one. The sky became less like magic and more like a set of forces that could be measured, tested, and eventually controlled. The first wing shapes were far from perfect. Kites, gliders, and experimental flying machines were built from wood, stretched fabric, wire, and a lot of trial and error. Some wings were nearly flat. Others were curved. Some were inspired by birds. Some rose for a moment and then failed just as quickly. A flat board angled into the wind can create lift, but it also creates a lot of drag and can make the airflow messy and unstable. A curved wing can guide air more smoothly, but the shape has to be right. If the curve is too crude or the angle is pushed too far, the air no longer follows the wing cleanly. It breaks away and the wing loses its grip. The common word for the cross-section of a wing is airfoil. It sounds like a lab term, but the picture is easy to understand. Imagine slicing through a wing from front to back and looking at the shape left behind. It usually has a rounded front edge and a thinner rear edge, built so the air can meet it without being torn into chaos. The air does not simply crash into the wing and bounce off. It flows around the surface, bends, speeds up, slows down, changes pressure, and leaves the back of the wing moving differently than when it arrived. This is the point where many simple explanations start to go wrong. One familiar version says the air traveling over the top of the wing has a longer path, so it has to move faster in order to meet the air traveling underneath at the trailing edge. It sounds neat, but the air does not work by that rule. Air particles passing above and below a wing do not make an appointment to reunite at the back. In real airflow, the air moving over the top often reaches the trailing edge sooner. The real explanation is not as tidy, but it is much more interesting. A wing creates lift because it changes the motion and pressure of the air around it. As the airplane moves forward, air rushes toward the wing. When the wing is tilted slightly upward at what engineers call an angle of attack, it turns part of that air downward. Behind the wing, the air has been given a downward motion known as downwash. Newton's laws describe what happens next. If the wing pushes air downward, the air pushes the wing upward. That upward reaction is lift, and it can be strong enough to raise tons of aircraft off the runway, but that is not the whole picture. The pressure around the wing tells the same story from another angle. Over the top surface, the air is guided along a curved path and often moves faster. In that faster-moving flow, the static pressure drops. Beneath the wing, the pressure is generally higher. The wing is not lifted only because air is slamming into the underside like a hand pushing up a tray. A large part of the lift comes from the lower pressure above the wing, with the higher pressure below helping drive the wing upward into that region. That does not mean the wing is being sucked into the sky by a vacuum. The air above the wing is still air. It still has pressure. But the wing has organized the surrounding flow into a pattern: lower pressure over the top, higher pressure below, and a wake behind it that has been turned downward. The Newton explanation and the pressure explanation are not competing stories. They are two ways of describing the same event. The wing rises because the air around it has been accelerated, curved, and rearranged. The big leap came when flight moved out of guesswork and into measurement. Wind tunnels, careful glider experiments, and the growing science of fluid motion showed that a wing could be refined instead of merely copied from nature. The Wright brothers are remembered not just for building a powered aircraft, but for testing wing shapes and control surfaces with unusual care. They understood that lift by itself was not enough. A machine that rises but cannot be controlled is not really flying. It is only delaying a crash. As engines became more powerful, wings had to evolve again. Faster airplanes needed stronger structures and more refined airfoil shapes. Metal gradually replaced much of the wooden fabric in serious aircraft construction. Designers learned that a wing could not be judged only by how much lift it made. It also had to carry fuel, hold spars, support landing gear, survive turbulence, reduce drag, handle different speeds, and behave predictably when pilots needed control most. Every smooth curve on a modern wing is part of a compromise between strength, efficiency, stability, weight, and safety. At takeoff, that compromise becomes easy to see. A large jet does not jump into the air. It earns lift with speed. The engines push the aircraft forward, the wheels race along the runway, and the wings begin moving through the air fast enough to matter. As the airplane reaches rotation speed, the nose rises. That small change increases the angle of attack. More air is turned downward. The pressure difference around the wing grows stronger. Lift builds until it becomes greater than the airplane's weight, and the tires finally let go of the runway. Then another part of the wing reveals itself. Flaps extend from the trailing edge, and on many aircraft, slats slide out from the leading edge. These surfaces temporarily reshape the wing, making it larger, more curved, and better at producing lift at lower speeds. This is especially important during takeoff and landing, when an aircraft is not moving as fast as it does in cruise. Without flaps and slats, many large airplanes would need much longer runways and would have to land at much higher speeds. A modern airliner wing is not really one fixed shape. It is a shape that changes when the airplane needs help the most. Once the aircraft climbs away and settles into cruise, the wing cleans itself up. Flaps retract. Slats tuck back into the leading edge. The busy mechanical shape used near the ground becomes sleek again. At high speed, the airplane can produce the lift it needs with a smaller angle of attack and far less drag. The wing is still turning air downward. It is still creating a pressure difference. It is still doing the same basic job it did on takeoff, only now it is doing it quietly and efficiently, hour after hour, above clouds, oceans, mountains, and sleeping cities. The reason wings look so different from one aircraft to another comes down to purpose. A slow training airplane may use a thicker, more forgiving wing that handles gently at low speed. A glider may have long, slender wings that pull lift from rising air with very little drag. A fighter jet may use thinner, swept wings designed for speed, quick response, and high-energy maneuvering. An airliner wing belongs to a different world. Heavy weight, long range, fuel economy, predictable handling, and safe performance near crowded airports. One surprising detail is that a wing can still create lift while upside down, as long as the aircraft holds the right angle of attack. Aerobatic airplanes prove this during inverted flight. Another surprise is that increasing angle of attack does not keep adding lift forever. Push it too far, and the smooth airflow separates from the wing. The pressure pattern collapses, lift drops away, and the wing stalls. A stall is not the engine stopping. It is the wing losing its clean hold on the air. Lift is not one hidden trick inside a curved wing. It is the result of shape, speed, pressure, and motion working together at the same time. An airplane rises because its wings make the air leave differently than it arrived.